13.2 is on the sign test. And the sign test as a flowchart. We start with assigning positive and negative signs and discard any zeros. Let n be equal to the number of signs. And then let the test statistic x equal the number of the less frequent signs, so either positive or negative. Then, do the sample data contradict the alternative? If that's a yes, we just automatically fail to reject the null hypothesis. If it's a no, then we check to see if the sample size is less than or equal to 25. If that's a no, then we convert the test statistic x to the test statistic z is equal to x plus 0.5 minus n divided by 2 divided by the square root of n divided by 2. And then find that the critical z values from table A2 in the usual way. Otherwise, we would find the critical value from table A7 if n is greater than 25. Then, is the test statistic less than or equal to the critical value? If that's a yes, reject the null hypothesis. If it's a no, fail to reject the null hypothesis. And to just state it out with much better wordage, we want to use the positive and negative signs to test a claim of falling into one of the following categories. Matched pairs, we subtract the second value of each pair from the first, record the sign of the difference, ignoring any zeros. Nominal data with two categories. We want to represent each member of one category by a positive sign, and represent each member of the other category by a negative sign. And then median of a single population, we subtract the median from each sample value, record the sign of the difference, and ignore any zeros. The disadvantage, though, is that the sign test only uses information about the direction of the data, ignoring the magnitudes of the data values, as the numbers themselves are dropped, other than the sign itself. We will let x be the number of times a less frequent sign occurs, and n the total number of positive and negative signs combined, no zeros. The requirement is the sample data is a simple random sample only. The test statistic is that if n is less than or equal to 25, the test statistic is x, the number of times the less frequent sign occurs, and we use table A7. If n is greater than 25, the test statistic is z is equal to x plus 0.5 plus n divided by 2, minus n divided by 2, excuse me. That should be a minus, not a plus. There we go. Minus n divided by 2 divided by the square root of n divided by 2. And then use table A2. The p-value can be provided by SAS, but it can often be found just using the z-test statistic if n is greater than 25. Because z is based on the less frequent sign, all one-sided tests are treated as if they are left-tail tests. So for example, among 945 couples who used the XSort method of gender selection, 66 had boys, so the sample proportion of boys is 66 out of 945, or 0.0698, based on data from the Genetics and IVF Institute. We want to consider the claim that the XSort method of gender selection increases the likelihood of baby boys, so that the probability of a boy is p is greater than 0.5, which becomes the alternative hypothesis. But, and let me just type this out so it's a bit easier for this, but we know that the sample proportion is 0.0698. We can never support a claim of the proportion of boys being greater than 0.5, since 0.0698 is so much less than 0.5. Since 0.0698 contradicts the alternative hypothesis. And as such, we wouldn't even bother to compute the actual sign test due to the fact that it's already contradicted, and such we could reject the alternative in favor of the null hypothesis. When we use the claim about matched pairs, when we're using the sign test with data that are matched pairs, we first convert the raw data to positive and negative signs, subtract each value of the second variable from the corresponding value of the first variable, then record only the sign of the difference. Exclude ties by deleting any matched pairs with both in which both values are equal. The main concept is if the two sets of data have equal medians, the number of positive signs should be approximately equal to the number of negative signs. So for example, let's say the table this table down here includes weights listed in dataset 10. Those weights were measured from college students in September and April of their freshman year. Using the sample data to test the claim that there is no difference between the September weights versus the April weights, we want to use the sign test with a 5% significance level. Now, due to the way this data set's actually coded, these are volunteered responses. So because of this being volunteered, we unfortunately have to then say that the assumption then is not met. But we're going to assume that it is for the sake of showing off the sign test. The null hypothesis is that there is no difference between the April and September weights. So no difference between April and September weights. This is where the median of those differences is equal to 0. The alternative is that there is a difference. There is a difference. This is where the median of those differences is not 0. So from this, we could toss this data set into SAS, which I already did, calling this data set freshman weights, which I have already put through up on here, showing the September and then the April weights right there as well. If we put that into SAS, we could first subtract the September and April weights in order to get the differences for these different signs. So I did data diff set work.freshman, which is why I called the freshman weight data set. Diff would be equal to September minus April. And then proc univariate data is equal to diff, and then run. Okay? Doing so, once it loads, the one that we are looking for is not the September or the April one. We want the difference. So the sign test is located in the tests for location section. It gives us a test statistic of negative 2.5, which and then gives us a probability here of 0.1797. Alright. So this gives us a test statistic M of negative 2.5 and a p-value of 0.1797. Now, if we did this by hand, our test statistic is actually positive 2. But we obtain the same type of answer based upon if we did this by hand or instead of SCS that we just did. And either way, again, we obtain the same answer, which is that we fail to reject the null hypothesis of no differences, which means that the median is indeed 0. Based upon that particular test. Now, involving nominal data with two categories, we can identify the proportion of the sample data that belong to a particular category, and then test claims about the corresponding population proportion P, and then label these values with a positive or negative sign as appropriate. Now let's say, for example, the Genetics and IVF Institute conducted a clinical trial of its methods for gender selection for babies. Before the clinical trials were concluded, 879 of the 945 babies born to parents using the X-sort method of gender selection were girls. Using the sign test and a 0.05 significance level to test the claim of this method of gender selection is effective in increasing the likelihood of a baby girl. So for this, we want to assume the requirement of this being a simple random sample. The null hypothesis is that the proportion is 0.05. And the alternative is that girls are more likely, which means the proportion is greater than 0.05. Alright, since we have an n of 945, x is defined by 945 minus 879. Tossing that into a calculator would give us a value of 86. Give us a value here of 86. And so because of that, our test statistic actually this gave us a value of 66, not 86. I read the wrong number. Gave us a value of 66. So our test statistic, because this sample size is, well, much greater than 25, we would use, and let me give myself more room to write this out. We would take that value of x, add 0.5, and subtract and divide by 2. This whole thing will be divided by the square root of n divided by 2. So in this case, this is going to be 66 plus 0.5 minus 945 over 2 divided by the square root of 945 divided by 2. Tossing this expression into a calculator would give us an answer of negative 26.41. Now, because this number is incredibly small, the critical value for this was negative 1.645. And this is incredibly small. So we could certainly say, and this falls well within that critical region, we could say without a doubt, that there is sufficient evidence to support the claim that goals are more likely with the XSort method. And then finally, for our last one on here, dataset 2 includes measured body temperatures of adults using the 106 temperatures listed for 12 a.m. on day 2 with the sign test to test the claim that the median is less than 98.6 degrees Fahrenheit. Of the 106 subjects, 68 had temperatures below 98.6 degrees Fahrenheit, 23 had temperatures above 98.6 degrees Fahrenheit, and 15 had equal to 98.6 degrees Fahrenheit. So we could say that this is a simple random sample. The null hypothesis for this is that the median is equal to 98.6 degrees Fahrenheit, and the alternative is that the median is less than 98.6 degrees Fahrenheit. We were told that n is 91, and the smaller values between 68 and 23 is of course 23. Now we could go about calculating this using that z-test statistic, and SAS, if we use those values, which is based upon the day 2 at 12 a.m. values, we could first subtract those. I'm calling this data set temperature, and we specifically just want the 12 a.m. for day 2, so set underscore temp 0 period underscore O2 underscore body underscore temperatures. Temperature is equal to day 2 underscore 12 a.m. And then proc univariate data is equal to temperature. Mu 0 is that this is equal to 98.6. And then 1. Doing so gives us a whole bunch of stuff. We don't care about that. We just care about this last one. And we could see that it gives us a sign here of 22.5, which is very close to the 23 here that we just got. And this gives us a p-value very small of less than 0.00001. So using SAS, we get an m-value of negative 22.5 and a p-value of less than, 0.001. 0.0001. I forgot a 0 in there. 0.0001. If we did this out by hand, we would need to use the test statistic z is equal to, this would be 23 plus 0.5 minus 91 divided by 2 divided by square root of 91 divided by 2. This gives us a value of about negative 4.61, which corresponds to this because the critical value is negative 1.645. And so we could write up our conclusion to this, and I'll just again type this so it's a bit easier for that. At the 5% level of significance, we have sufficient evidence to support the claim that the median body temperature of healthy adults is less than 98.6 degrees Fahrenheit. Let me know if you have any questions or concerns. Thank you.